All right, this is the first section that we're doing in Unit 3. We're skipping sections 4.1 and 4.2, going right into derivatives. 4.1 and 4.2 it's just a review of some of the things you learned from 1050 regarding exponentials, how to graph them, how to work with properties of exponents, how to solve exponential equations, things like that, that we'll use to some degree. But the main focus of Unit 3 is to find a derivative of exponential functions like we're doing in this section, and then in section 4.5 to find the derivative of the logarithmic function. So we are going to start with just the definition of, a reminder I guess, of the exponential function, and how we're going to use it in this unit. So an exponential function, if you remember from 1050, has a base that's a number. In this case, we're going to use the number e, and then the variable is in the exponent. So that's the natural number e, and this is the primary exponential function we're going to use. We may mess around in a little bit with exponential functions of other bases, but for right now we're going to stick to e to the power of x. Now the definition, the derivative f prime, well, let's do this. Let me back up. So the derivative with respect to x of e to the x, this one's an easy one. The derivative of e to the x is e to the x. Now we're going to expand that using the chain rule. The derivative with respect to x of e to the u, where u is an expression of x. So u could be something like x squared, or 2x, or 5x squared minus 3. U just represents an exponent that is a function of x. So the derivative of e to the u is e to the u, but as you're familiar with the chain rule, that's the derivative of the inside part. Excuse me, that's the derivative of the outside function, e to the u. Now we need to multiply that by the derivative of the inside part. So it's e to the u times du, where du is the derivative of this exponent right there. And this one is the one we're going to be seeing most of. It's the derivative of the exponential function by using the chain rule. So a few easy examples to start out with. Find the derivative. So for part A, let's see, f of x equals e to the 3x. Let's do a part B. F of x equals 3 times e. Just comparing these two. So for part A, the derivative e to the 3x, that's going to follow that rule right there where u is equal to 3x. So actually my notations aren't matching, so let me do a quick fix. Let's stick with function notations. Let's find f prime of x. So f prime of x is the derivative of e to the 3x. And like I said, we're going to use that as our pattern. The derivative of e to the u is e to the u. So the derivative of e to the 3x is e to the 3x. But then we multiply that by the derivative of u, in this case the derivative of the exponent the derivative of 3x is 3. So that's 3e to the 3x. Now for part B, the derivative this one's kind of a trick question. You need to go back and remember one of the very first properties of derivatives we learned back in chapter 2, that the derivative of a constant is 0. This expression, 3 times e to the first power, is a constant. It's no different than the number 2 or the number 10 or 100. The derivative of a constant is 0. 3e to the x is a constant. There's no variable, so it's not technically an exponential expression. It's just a constant. The derivative of a constant is equal to 0. You will typically find on your homework as well as on the exam for Unit 3 that the property we're learning here of the derivative of e to the u is going to be combined with other properties of or types of derivatives like the product rule or quotient rule. For example, x squared times e to the 2x plus 1. So there's a product. We have one function multiplied by another function, so using the product rule that we learned back from Unit 1, it's the derivative of the first function multiplied by the second function plus the derivative of the second function. Now, this function right here, e to the 2x plus 1, we can consider it as e to the u, and the derivative of e to the u is e to the u, or in this case, e to the 2x plus 1, but then we need to multiply it by the derivative of u, or the derivative of the exponent. The derivative of 2x plus 1 is 2. So we've got, if we want to use the f and g notation that we learned back in chapter 2, f prime times g plus g prime, that whole thing right there is g prime, so now we need to multiply that by f. So we have 2x e to the 2x plus 1 plus 2x squared e to the 2x plus 1. Now, if we look at both of those expressions, there are common factors. So if we pull out a 2x and an e to the 2x plus 1, that leaves 1 plus x. Let's try one. You'll have one similar to this on your homework of a quotient rule. So f of x let's say e to the x plus e to the negative x over 2. At first glance, you may think, okay, this is going to be a quotient rule because we have a numerator and a denominator. But like we talked about several times, this expression has several terms in the numerator, but one single term in the denominator. So you could think about this as separate fractions, and then you even go one step further. Rather than dividing it by 2, you could multiply it by 1/2 and consider the 1/2 as a coefficient. So we've got a new form of f of x. that I think will be easier to differentiate, because we can differentiate now separate terms. So the derivative f prime of x, if we think about this first term here, 1/2 times e to the x. 1/2 is just a coefficient, so it's going to stay a coefficient. If we think about the derivative of e to the x, we talked about this right at the beginning of the lesson, the derivative of e to the x is just e to the x. So the derivative of that first term stays the same as the original expression, 1/2 times e to the x. Now, moving on to the second term here, 1/2 again is a coefficient, and then the derivative of e to the negative x is e to the negative x, but this is not a chain rule since we have an inside function, negative x, so we need to multiply that now by the derivative of the inside function, which is negative x. The derivative of negative x is -1. So we have 1/2 e to the x minus 1/2 e to the negative x. If we wanted to simplify, we could factor out a 1/2 and say it's e to the x minus e to the negative x. So that one didn't actually need the quotient rule, but I'm pretty sure there's a few in your homework where you are going to need it. For example, let's do numerators e to the 2x and denominators e to the 2x plus 1. So using the quotient rule, I'm going to start with the denominator because it's the easiest to remember. The denominator is just whatever the denominator of the original function is squared. Okay, and then in the numerator we have the bottom function times the derivative of the top function, and the derivative, I'm talking about this top function, the derivative of e to the 2x is e to the 2x, but since we have an inside function, we do a chain rule, so it's multiplied by the derivative of that, minus the top function multiplied by the derivative of the bottom function. And since it has multiple terms, we think about the derivative of each term. Now the derivative of e to the 2x is e to the 2x, but since it has an inside function, which is the 2x, we multiply it by the derivative of that inside function. The derivative of 2x is 2. And then the derivative of 1 is just 0. So using the same terminology that was introduced back in Unit 2, or Chapter 2 rather, this is the low function. So low d high minus high d low all over low squared. That's the terminology I used when first introducing the quotient rule there. So simplifying would be distributing in the numerator. So we could take this term, multiply it there, and take that term and multiply it there. So e to the 2x multiplied by, or rather 2, I got to carry this 2 with it, so 2 times e to the 2x multiplied by e to the 2x. Well, when you're multiplying terms that have the same base, you add the exponents. So that's 2e to the 4x. And then when this term multiplies there to the 1, it's 2e to the 2x minus, now we're multiplying here, And again, since we have the same base, we're going to add the exponents. So it's e to the 4x. You know what? We've got to get that 2 there with it, so minus 2e to the 4x. So we're not really distributing, we're just combining those two, multiplying. So the e to the 4x can cancel. So we have 2e to 2x over e to 2x plus 1 squared. Now, some of the other types of questions you're going to encounter on the homework would be to use this rule of differentiation, but rather than just finding the derivative, you're going to apply it by finding the either the slope of a tangent line at a point or even an equation. When given a point, the equation of a tangent line. So for example, if we have find the equation of a tangent line at the given point. So if we had a function and then the point given was -1 and then e cubed. So we first have to find the derivative, g prime, and that's going to allow us, I think that's going to allow us to find the slope of the tangent line at that point, and then we could find the equation. So, g prime. We're going to use the same rule, the derivative of e to the u. In this case, this is u, is e to the u. But then we need to multiply it by du, or the derivative of the inside part. So it's going to be 3x squared minus 4. So if we wanted to simplify this a little bit, we could distribute this term to that and to that. So we're going to have 3x squared e to the x cubed minus 4x minus 4e cubed. So that's the derivative. Now the derivative is a function that can tell us the slope of the tangent line at a given x value. The given x value is -1, so we need to plug -1 in for all the x's. So the value of the derivative at -1 would be plugging -1 in for all the x's. So right here, -1 squared is 1, so that's 3. And then e, and then right here, -1 cubed is -1, and that's a plus 4. -1 plus 4 is 3, so 3e cubed minus 4, and then again, -1 cubed is -1, and then that's plus 4. Whoop. So -1 plus 4 is 3, so we've got 3e cubed minus 4e cubed, so that's -e cubed. So the slope of the tangent line is negative e to the third power. That's our slope. Now it wants the equation of a tangent line and it needs to be of the form y equals mx plus b. Well, the slope that we just found goes in place of m, because that's the slope. And then for an x and a y, we can use the given point. That's the x value and that's the y value. So those can replace the x and the y. So if I plug in all of those values, e to the third from this y value right there equals negative, and that's from this slope value right there, and then times x. Now the only value that we didn't know was the y-intercept, that b value, but now we can find it because we have an equation here with only one variable. So negative times a negative is positive, so we've got e cubed equals e cubed plus b. Well, this just tells us that b is equal to 0. So the equation is y equals negative e to the third, because that's our slope, times x. And there is no plus b because it's just plus 0, which we don't need. Right there. All right, last type of question you're going to see would be finding the derivative implicitly, which was back in chapter 2, 2.7, I think. So find the derivative using implicit differentiation. Now, just in case you've forgotten, let me come over here. Let's say we have the derivative with respect to x of an expression 4x squared minus 5y cubed. Now, even though it might not explicitly say find the derivative using implicit differentiation, what you need to start remembering and looking for is we're taking the derivative with respect to x of a variable that doesn't match. So, well, these variables here match, so that's just normal differentiation. The derivative of 4x squared is 8x. Now, the derivative of 5y cubed is 15y squared, but this is implicit differentiation, which is really just an application of the chain rule. Y represents an inside function of x, so this right here would be the derivative of the outside part. Now we need to multiply this by the derivative of the inside part, which is dy dx. So this is what we did back in section 2.7 using implicit differentiation. So the only thing that's going to be different now is it's going to have exponentials, base e exponential, for example. So the example might be something like x squared times y minus e to the y minus 4 equals 0, and you're supposed to find dy dx. So we're just going to go one term at a time and take the derivative. This one is going to not only require implicit differentiation because of the y, but it's also a product rule. It's x squared times y. So we're going to have to do our product rule, which is the derivative of the first function times the second function plus the derivative of the second function. The derivative of y with respect to x is just dy dx times the first function, so that's the product rule. Now we subtract the derivative of this. The derivative of e to any exponent is e to that exponent, but now we have a chain rule. Y represents an inside function, so we need to multiply it by the derivative of the inside function, which is dy dx. Now the derivative of that -4 is 0, and then the derivative of 0 is 0, so this equals 0. At this point, any term that has a dy dx factor, like this term and that term, those both have dy dx factors, so I'm going to keep them on the left side. This term doesn't have a dy dx, so I'm going to subtract it over here to that side. So now I'm going to have dy over dx times x squared minus e to the power of y dy dx equals -2xy. Now both of these terms that I've left alone on the left side have a dy dx as a common factor, so that can be factored out. And then you can divide by this onto the other side to get dy dx by itself. And that's pretty good sampling of the homework questions or typical test questions you would see from this section.